Please subscribe to support the channel. Astronomers estimate there are around 2 trillion galaxies in the observable universe, the portion of the cosmos from which light has had time to reach us since the Big Bang, about 13.8 billion years ago. This boundary isn't a limit of our telescopes, but of light itself. Beyond it, galaxies exist whose light will never reach Earth because the universe is expanding faster than light can travel. The observable universe stretches about 93 billion light-years across, containing a mind-bending number of galaxies, each with its own billions of stars, worlds, and perhaps even life. And yet, this is only what we can see. The true universe almost certainly extends far beyond, into regions forever hidden from us. Each of those trillions of galaxies we just spoke about isn't just a distant smudge of light. It's an entire cosmic ecosystem, a self-contained island of matter, energy, and time. A galaxy is not a single object, but an intricate collection of hundreds of billions of stars, along with their planets, moons, nebulae, gas clouds, dark matter, and often a supermassive black hole at its center. It's a city of stars, a gravitational masterpiece shaped over billions of years. The Milky Way, our home galaxy, contains around 100 to 400 billion stars, though astronomers still debate the exact number. That's the average range for a galaxy. But galaxies can vary enormously. Some tiny dwarf galaxies may hold only a few million stars, while giant elliptical galaxies, like those at the centers of galaxy clusters, can host more than 1 trillion. In other words, galaxies are like cosmic snowflakes. No two are exactly alike, and their scales stretch across unimaginable ranges. When we say that each galaxy contains around 100 billion stars, that number alone sounds incomprehensible. But to make it tangible, imagine this. If you were to count one star per second, non-stop, day and night, it would take you over 3,000 years to finish counting just the stars in one galaxy like ours. Now multiply that by 2 trillion galaxies, and the human mind simply collapses under the weight of those numbers. We're talking about hundreds of billions of stars in each of trillions of galaxies, a cosmic arithmetic that exceeds all meaning. And these stars come in a dazzling spectrum of forms. There are young, hot blue giants that burn through their fuel in a few million years, and ancient red dwarfs that quietly shine for trillions. Some stars are orbited by entire systems of planets and moons, while others drift alone through interstellar space. Surrounding many are clouds of dust and gas, stellar nurseries where new suns are born in shimmering curtains of light and plasma. Galaxies are not static pictures frozen in time. They are alive in a cosmic sense, continuously giving birth to new stars while older ones die, explode, and seed the next generation with heavy elements, the ingredients for life. But a galaxy isn't just made of stars. Between them lies the interstellar medium, a diffuse mix of gas, dust, and magnetic fields. This material might seem empty to us, but it's the raw fuel for future generations of stars. When gravity compresses these vast clouds, they collapse, ignite, and new suns are born. Over millions of years, these cycles of death and rebirth have sculpted galaxies into the structures we see today. Spirals, ellipses, and irregular forms swirling through space like cosmic art. Yet the visible matter, everything we can see, accounts for only a tiny fraction of a galaxy's true mass. Surrounding each one is a dark matter halo, an invisible gravitational skeleton that holds it together. Without it, galaxies would spin apart. This means that most of what makes a galaxy isn't even visible to us. The luminous stars, the nebulae, the radiant arms, all of that is just the glittering surface of something far more massive and mysterious beneath. Now consider the full cosmic multiplication. If one galaxy contains on average 100 billion stars, and there are roughly 2 trillion galaxies in the observable universe, then multiplying those two figures gives us 200 billion trillion stars. That's 200 sextillion stars, a 2 followed by 23 zeros. Each of those stars could have planets, Many do. In fact, modern astronomy has revealed that planets are common, not rare. On average, there may be more planets than stars in the universe. This means that in every galaxy, there may be hundreds of billions of potential worlds, some gas giants, some icy dwarfs, and perhaps even millions that are Earth-like, orbiting their suns in the delicate balance that allows for liquid water and maybe life. And when we truly absorb this, the enormity hits us. Every pinprick of light in the night sky represents just one star in our galaxy. But beyond them lie countless other galaxies, each filled with their own suns, their own planets, and perhaps even their own stories. It's not just that the universe is big, it's that it's unreasonably big, overflowing with creation on a scale that challenges everything we think we understand about our place in existence. And yet, all of these galaxies, massive collections of matter, light, and time, are only the building blocks of something even greater. Because when we multiply these numbers, when we start to grasp what 2 trillion galaxies truly means, we confront a scale that borders on the infinite. The next step then is to take that unimaginable count and do the math, to see, numerically, just how vast the cosmos truly is. Now that we've grasped what a single galaxy contains, let's confront the true mathematical magnitude of the universe. The moment where numbers stop behaving like quantities and start to feel like infinity itself. If the average galaxy contains around 100 billion stars, and there are roughly 2 trillion galaxies in the observable universe, then multiplying those two figures gives us 200 billion trillion stars. That's 200 sextillion stars, a 2 followed by 23 zeros.
Pause on that for a moment. Try to let it settle in, because that number isn't theoretical. It's what's actually out there, what really exists, what really shines in the vastness of space. 200 sextillion suns, each one potentially surrounded by planets, moons, and all the physics and chemistry that make up the story of the cosmos. To put that into perspective, scientists have tried to compare this astronomical figure to something familiar: the grains of sand on all of Earth's beaches. From the tiniest dust on the shores of a tropical island to the sweeping dunes of deserts like the Sahara, it's estimated that there are roughly 7.5 quintillion grains of sand on Earth. That's a 7.5 followed by 18 zeros, a number so large it already feels uncountable. But the number of stars in the observable universe surpasses that by tens of thousands of times. In other words, if every grain of sand on Earth represented a star, the universe would still need tens of thousands more Earths covered in sand from pole to pole just to represent the total number of suns out there. And remember, this figure, 200 billion trillion, is only for the observable universe, the part of the cosmos from which light has had time to reach us. The true universe, beyond our cosmic horizon, could contain countless more galaxies, perhaps infinitely more. Which means that even our most mind-stretching numbers are likely a fraction of reality. Each of those 200 sextillion stars burns with its own story. Some are tiny red dwarfs that will shine faintly for trillions of years, longer than the universe has existed so far. Others are massive blue-white giants that live fast and die young, ending their lives in violent supernova explosions that scatter heavy elements into the interstellar void. Some stars are solitary, while others exist in binary or even trinary systems, orbiting one another in a delicate gravitational dance. Each is a sun in its own right, some warming worlds, some surrounded by swirling disks of dust where new planets are being born. This multiplication, 2 trillion galaxies, each with 100 billion stars, doesn't just reveal a number, it reveals an idea that the cosmos is not sparse, but overwhelmingly abundant. It overflows with creation, redundancy, and possibility. Wherever we look, on whatever scale we observe, we find repetition and diversity woven together, an infinity of lights in an infinity of distances. Imagine standing on a beach at night. You scoop up a handful of sand and look at the countless grains trickling through your fingers. Now, in your mind, turn every one of those grains into a star. Then imagine every beach on every continent, every desert, every grain of sand that's ever existed, and multiply it again and again. Still, you wouldn't reach the number of stars shining in our observable cosmos. It's humbling beyond words. This realization doesn't just make Earth feel small. It transforms our entire perspective. Every human story, every civilization, every planet we know, it all exists around a single star among 206 trillion others. And each of those other stars could have its own stories, its own histories, its own versions of us looking out at their night skies, wondering if anyone else is out there. In the language of the cosmos, we are one note in an infinite symphony. And yet, knowing this doesn't diminish us. It connects us. Because in understanding how vast and full of stars the universe is, we begin to sense something deeper. That existence itself is an ocean of possibilities. And we are part of that ocean, not separate from it. But how do we come to know this? How did humanity, standing on a tiny planet under one sun, come to realize that the universe holds trillions upon trillions of galaxies? The answer lies in one of the most profound moments in the history of science. A moment when we dared to look into what seemed like nothing and discovered everything. When humanity first built the Hubble Space Telescope, it was like opening a window into the cosmos that had been painted shut for all of human history. Orbiting above Earth's atmosphere, Hubble could see farther, clearer, and deeper into the universe than any telescope before it. But the true power of that telescope wasn't revealed until astronomers decided to do something that at the time sounded almost absurd. They pointed Hubble at what seemed to be nothing. In 1995, scientists selected a tiny, random patch of sky near the constellation Ursa Major. A patch so small that if you held a single grain of sand at arm's length, that speck would completely cover it. Through every telescope on Earth, that region looked perfectly empty. No bright stars, no visible galaxies, just void. Yet, astronomers wanted to know, was it really empty, or was there something hidden there too faint for any previous instrument to detect? So they instructed Hubble to stare into that dark spot for more than 10 consecutive days, capturing every photon of light it could. This was a massive gamble. Telescope time is incredibly valuable, and devoting so much of it to what appeared to be a blank section of sky was controversial. Many in the scientific community thought it was a waste of effort. But when the data finally came back, the universe itself rewrote our expectations. What emerged from that darkness was one of the most jaw-dropping images ever captured, the Hubble Deep Field. In that tiny patch of sky, no larger than a pinpoint on your fingertip, Hubble revealed thousands of galaxies, each one containing hundreds of billions of stars. Every smudge, every colored swirl in that image wasn't a star, it was an entire galaxy, millions or billions of light years away. This discovery was nothing short of a revelation. It proved, beyond any doubt, that the universe was far more crowded and far more vast than anyone had truly imagined. That single image suggested that if a patch of sky that small could contain thousands of galaxies, then the entire observable sky, if mapped at the same resolution, would contain trillions. It was the visual confirmation of what had previously been theory, that galaxies are scattered across the cosmos in all directions, filling the universe like stars fill the night sky. Each galaxy captured in the Hubble Deep Field represented a different era of cosmic history. Some of the galaxies were so faint and distant that the light reaching Hubble had traveled for over 13 billion years, meaning the telescope wasn't just looking across space, but back through time, glimpsing the universe as it was when it was still young. Others were relatively closer, showing the full diversity of galactic evolution, from small, chaotic star-forming blobs to majestic spiral and elliptical shapes. What's even more astonishing is that the Hubble Deep Field wasn't unique. Astronomers repeated the experiment several times in different parts of the sky: the Hubble Ultra Deep Field, the Extreme Deep Field, and others. And every single time, the result was the same. The sky was overflowing with galaxies, even in the darkest, most empty places. There were no barren directions, no cosmic voids free of galaxies, only vast distances between them. The entire observable universe was a three-dimensional sea of galaxies, stretching across the sky in every conceivable direction, each one teeming with stars, planets, and cosmic history. It's almost poetic how this challenges our instinctive sense of isolation. When we stand under the stars, it's easy to imagine that the points of light above us are rare, that the darkness between them dominates the universe. But the opposite is true. The darkness isn't empty, it's simply too distant and too faint for our naked eyes to detect. Beneath that apparent blackness lies layer after layer of galaxies, so numerous that if our eyes could perceive all wavelengths of light, the night sky would glow with a soft, endless radiance.
To get a sense of this, imagine slicing through the universe in any random direction, upward, downward, sideways, and stretching that line out for billions of light years. Along that line, you would pass galaxies scattered like pearls on a cosmic string. Some would be close to one another, bound together in clusters or superclusters. Others would drift alone, solitary wanderers in the dark. But you would never travel far without encountering more. Even in regions astronomers call voids, where galaxies are relatively sparse, there are still some, just fewer than average. There are no galaxy-free zones, no cosmic deserts completely devoid of structure. This all-encompassing presence of galaxies is one of the most visually stunning ideas in all of science. Every galaxy we see is like a small spark in a vast cosmic firework. When we look up, we're not just seeing light from our own corner of space, we're seeing photons that have traveled for billions of years from countless other galaxies, across unimaginable distances, through expanding space to finally reach our eyes or our telescopes. Each one is a messenger from a different era of the universe's history. Even more awe-inspiring is that galaxies don't cluster in random chaos. They follow patterns, massive web-like structures called cosmic filaments, where galaxies and clusters of galaxies form interconnected threads stretching across the universe. Between these threads lie gigantic cosmic voids, regions with fewer galaxies, but even these are not truly empty. In every direction, these filaments and voids weave together into an enormous cosmic web, the architecture of the universe itself. When the Hubble Deep Field image revealed thousands of galaxies in what seemed like nothingness, it forced astronomers to confront the staggering uniformity. Every subsequent observation, from Hubble's successors to ground-based telescopes like the Very Large Telescope and Keck Observatory, confirmed the same conclusion. There are galaxies in every single direction we can look, from the nearest reaches of intergalactic space to the very edge of the observable universe. And this uniformity, this cosmic sameness, is one of the fundamental pillars of modern cosmology. It's called the cosmological principle, and it states that the universe is homogeneous and isotropic on large scales. In simpler terms, that means it looks roughly the same everywhere, no matter where you are or which way you look. To any observer in any galaxy, the universe would appear as if galaxies stretched endlessly around them in all directions. There is no cosmic center, no privileged vantage point. Every point is just as ordinary and extraordinary as every other. That truth is quietly humbling. It means that the Milky Way isn't in a special location. We are not at the center of anything. We are one of countless galaxies floating in an even vaster expanse, each a tiny spark in the cosmic night. And yet, despite this enormity, the fact that the universe appears similar from every angle speaks to an elegant simplicity beneath all that chaos, a kind of cosmic symmetry that binds everything together. So when we gaze up at the night sky and see only a few thousand visible stars, we're witnessing only the tiniest fraction of what's really out there. Beyond those stars are billions more hidden in the vast depths of other galaxies. Beyond those galaxies lie still more, stretching outward until the light itself can go no farther. Every direction, every piece of sky, every point in space, filled, alive, luminous. And with every distant galaxy we glimpse, we're also looking backward in time, peering into the ancient past. Because light, no matter how fast, takes time to travel. And the farther we look into the universe, the older that light becomes. In the next step of our journey, we'll explore this breathtaking concept, how looking out into the universe is also looking back through time itself. When we look up at the night sky, we're not seeing the universe as it is. We're seeing it as it was. Every glimmer of starlight, every faint galaxy captured by a telescope is a message from the past, carried across billions of years through the vastness of space. Light, for all its incredible speed, 300,000 kilometers per second, still takes time to travel. And the deeper we look into the cosmos, the farther back in time we're peering. This is one of the most beautiful and mind-bending truths in all of science. The universe is a time machine, and telescopes are our portals into its history. When you gaze at the moon, you're seeing it as it was 1.3 seconds ago. The light from the sun takes about 8 minutes to reach Earth, which means that if the sun were to suddenly disappear, heaven forbid, we wouldn't even know for those 8 minutes. When we look at the nearest star system, Alpha Centauri, we're seeing light that left it over 4 years ago. But now imagine looking beyond our Milky Way, beyond nearby galaxies like Andromeda. When we look at distant galaxies billions of light years away, the light reaching us today has been traveling through expanding space for billions of years. Those galaxies appear not as they are now, but as they were in the ancient universe, when stars were first beginning to form and the cosmos was still young. The farthest galaxies ever observed by the James Webb Telescope date back to when the universe was less than 400 million years old, just 3% of its current age. The light from those galaxies has been traveling for more than 13 billion years to reach us. So when Webb captures their faint glow, it's literally photographing ancient history, light that began its journey before our planet even existed, before our sun was born, before the Milky Way itself had fully formed. What's truly astonishing is that those galaxies no longer look like what we see. The universe has expanded dramatically since that light began its journey. Those galaxies have moved billions of light years farther away in the meantime, evolving, colliding, changing shape, perhaps even ceasing to exist altogether. But the photons that left them so long ago have been racing toward us, crossing unimaginable gulfs of time and space, arriving here only now, as silent travelers bearing the story of the early cosmos. This means that every direction we look in the night sky is filled with ancient light. The farther we look, the older that light is, until we eventually reach the faint afterglow of the Big Bang itself, the cosmic microwave background, the oldest light in existence. That faint radiation, stretched into microwaves by 13.8 billion years of cosmic expansion, is the universe's baby picture, a snapshot of when everything was still dense, hot, and glowing. The idea that we can see time itself frozen in light is both humbling and haunting. It reminds us that the universe is not static. Everything we see in the sky, the galaxies, the stars, even the constellations, are moments captured in light, not the present reality. If we could see them as they are now, most of them would have changed dramatically. Stars would have burned out, new ones would have ignited, galaxies would have merged and reshaped themselves. We live inside a cosmic movie, but we can only see the earlier frames, never the full unfolding in real time. In a sense, every observation in astronomy is an act of archaeology on a universal scale. Instead of digging into layers of soil to uncover ancient fossils, astronomers dig into layers of time, peeling back the history of the cosmos one photon at a time. Each telescope image is a fossil record of light, preserving moments that happened billions of years before life arose on Earth.
So when you stand under a clear night sky, realize this. You are surrounded by the past. Every star, every galaxy, every faint smudge of light is a ghost from another era. The sky above isn't just a view of space, it's a window into time. You are seeing light that began its journey before your ancestors walked the Earth, before Earth even cooled from molten rock. And yet that same light still finds its way to your eyes, bridging billions of years to whisper the story of creation itself. It's as if the universe has spent eons sending us messages, and only now do we have the tools to read them. But not all of those messages will ever reach us. Some galaxies are simply too far away, their light forever out of reach. Not because our telescopes aren't powerful enough, but because of a deeper cosmic limit. Space itself is expanding, stretching faster than light can cross it, creating a cosmic horizon beyond which we can never see, not now, not ever. Because the universe is expanding faster than light can travel through it. To understand this, we need to step back and remember something remarkable. Space is not static. The universe is expanding. Every second, the fabric of space stretches a little more, carrying galaxies along with it like raisins in a rising bread dough. This isn't galaxies moving through space, it's space itself expanding between them. And while nothing can move through space faster than light, there's no such speed limit on the expansion of space itself.
This means that far enough away, galaxies are receding from us faster than the speed of light. Not because they're breaking the cosmic speed limit, but because the space between us and them is stretching so rapidly that light from those galaxies can never bridge the gap. No matter how long we wait, their photons will never arrive. They're effectively slipping away, lost beyond a boundary that no signal or message can ever cross. This is the cosmic horizon, the edge of our observable universe. It's not a physical wall or a barrier in space, but a limit in time and causality. Anything beyond that horizon is forever disconnected from us. We can't see it, measure it, or interact with it in any way. It's not that those regions don't exist, they do, but they are sealed off from us by the relentless expansion of the cosmos. Right now, that observable region extends about 46.5 billion light-years in every direction. Everything within that sphere is part of the universe we can, in principle, observe. But beyond that, there's more, vastly more. The universe could extend hundreds of billions of light-years farther, or it could be infinite. We simply don't know. What we do know is that the unobservable universe, everything beyond our cosmic horizon, is likely far larger than the observable part, containing untold trillions upon trillions of galaxies that we will never see. It's an almost heartbreaking realization. There are entire regions of the cosmos, unimaginably vast stretches of galaxies, stars, and possibly civilizations that will remain forever hidden from us. Even if we could travel at the speed of light, we could never reach them. The expansion of space ensures that the distance between us grows faster than we could ever close it. Every second, more galaxies slip beyond the horizon, lost to eternity. The deeper the universe expands, the more isolated we become. In fact, this is already happening. The light we see from distant galaxies today comes from a time when they were much closer to us. But as the universe continues to expand, many of those galaxies are now receding faster than light, meaning that if we were to somehow wait long enough, billions upon billions of years, they would fade completely from view. The photons they send out now will never reach us. Over cosmic time, the universe will grow emptier and darker from our perspective as more and more galaxies redshift out of visibility. This expansion is not slowing down, it's accelerating, driven by something mysterious called dark energy, a force that seems to push space apart with increasing strength. Because of this acceleration, the cosmic horizon is effectively a one-way veil. Light can cross from beyond the horizon into our universe only if it was already on its way billions of years ago. Anything beyond it now is permanently beyond reach. The implications are staggering. The 2 trillion galaxies we estimate in the observable universe are just the beginning, a small sample of the total cosmic population.
There could be tens, hundreds, or even infinitely many trillions more galaxies beyond what we can see, spread across the boundless expanse of existence. If the observable universe were the size of a grain of sand, the unobservable part might stretch farther than all the oceans on Earth combined. So when we talk about the universe being filled with galaxies, we must remember that our numbers describe only the visible portion of an incomprehensibly larger reality. We live inside a tiny luminous bubble surrounded by a cosmic ocean that we can never explore, a boundary not defined by our limitations, but by the very geometry of space-time. This understanding reshapes our sense of what universe means. It's not just everything we can see, it's everything that exists everywhere, even if most of it will forever remain invisible. The cosmic horizon is both humbling and haunting. It reminds us that our knowledge, vast as it seems, is only a glimpse through a small window in an infinite cathedral. And yet, within that window, we found enough to fill our imagination forever. Trillions of galaxies, hundreds of billions of stars each, and the promise of worlds uncounted. And as we continue exploring, we find that even within our small observable patch, the diversity of those galaxies is extraordinary. They come in every shape, size, and age imaginable, a cosmic zoo of spirals, ellipses, and irregular wonders, each telling a different story of how the universe builds itself. Across the observable universe's unimaginable expanse, the 2 trillion galaxies we've spoken of are not all the same. Each one is the unique work of cosmic art, some elegant and symmetrical, others chaotic and raw. Just like no 2 snowflakes are identical, no 2 galaxies share the exact same shape, structure, or history. Yet astronomers categorize them into broad families, a way to make sense of this dazzling diversity. The 3 main types are spiral galaxies, elliptical galaxies, and irregular galaxies. Together, they paint the story of how the universe evolved, from turbulent beginnings to graceful maturity. Let's begin with the spirals, perhaps the most iconic of all. Spiral galaxies are the grand showpieces of the cosmos, the elegant pinwheels we see in textbooks and telescope images, with sweeping arms curling gracefully from a central core. Our own Milky Way is one of them, as is our nearest large neighbor, Andromeda. Spirals are places of ongoing creation. They're rich in gas, dust, and molecular clouds, the raw ingredients from which new stars are continuously born. The spiral arms, glowing with clusters of young blue stars, trace the waves of density rippling through the galaxy's disk. These arms aren't rigid structures, they're more like traffic jams in space, where material bunches up and triggers waves of star formation as it orbits the galactic center. The cores of spiral galaxies, on the other hand, tend to host older, redder stars, the ancient residents of the galaxy that have burned quietly for billions of years. Some spirals have smooth, tightly wound arms, others are more open and loosely coiled. Many even have a bar-shaped structure of stars cutting through the center, forming what astronomers call barred spirals, a category that includes our own Milky Way. This diversity in spiral forms hints at their dynamic lives, constantly rotating, evolving, and interacting with neighboring galaxies through gravity's invisible dance. Then there are the elliptical galaxies, massive, rounded, and smooth, like cosmic orbs of starlight. They are the old souls of the universe, filled mostly with ancient stars and very little gas or dust. Unlike the flat disc-shaped spirals, ellipticals are more like 3-dimensional spheres or elongated footballs, with stars orbiting in all directions rather than along an organized plane.
Elliptical galaxies are thought to form from collisions and mergers, when 2 or more galaxies crash together and their stars are thrown into new random orbits. Over time, these violent interactions erase any spiral structure, leaving behind a smooth, featureless glow. Because they lack the gas needed to form new stars, ellipticals are often quiet and dim in ultraviolet light, a sign that star birth has largely ceased. Yet many are truly enormous, containing trillions of stars and dominating the centers of galaxy clusters like giant cosmic monarchs surrounded by smaller companions. Finally, we come to the irregular galaxies, the cosmic misfits that defy easy classification.
They are galaxies without clear shape or structure, often warped and twisted by gravitational interactions or the after effects of collisions. Some are small, chaotic star-forming regions bursting with activity. Others are remnants of galaxies torn apart by tidal forces. Despite their unruly appearance, irregular galaxies are crucial to understanding the universe's history. They represent youth and disruption, snapshots of galaxies caught mid-evolution, still finding their form. Many irregulars are dwarf galaxies, far smaller than giants like the Milky Way. Some may only have a few billion stars, tiny by galactic standards, but they're often packed with gas and actively forming new stars at furious rates. They serve as the raw material for larger galaxies, merging over time to build the grand spirals and ellipticals we see today. In fact, astronomers believe that in the early universe, almost all galaxies began as irregulars, small turbulent clouds of stars and gas that gradually merged and evolved into more structured systems. What's truly astonishing is how these types, spiral, elliptical, and irregular, don't just represent different shapes, they represent different epochs and environments in cosmic history. Spirals are the fertile, star-forming galaxies that still glow with youth. Ellipticals are the ancient giants, the remnants of galaxies long past their most creative era. Irregulars are the wild and unpredictable ones, often caught in transition between those two states. And within each type lies more diversity still. There are miniature versions of each, dwarf spirals, dwarf ellipticals, and dwarf irregulars, dotting the cosmos like starlit pebbles. There are lenticular galaxies, hybrids that sit between spirals and ellipticals, with disk-like shapes but little gas or star formation. There are even ultra-diffuse galaxies, ghostly giants with so few stars that they're barely visible at all, held together mostly by dark matter. If you were to travel across the observable universe, hopping from one galaxy to the next, you would encounter an endless variety of cosmic environments. Swirling spirals with brilliant blue arms, massive ellipticals glowing like ancient embers, chaotic irregulars flashing with the light of newborn stars. Every galaxy would tell a different story, a story of creation, destruction, and transformation written in starlight. This vast diversity is a reminder that galaxies are not static decorations scattered across space. They are living systems, evolving over billions of years, shaped by gravity, collisions, and cosmic chance. Each one is a snapshot in time, caught in the endless process of becoming something else. And these transformations, these cosmic interactions, aren't just theoretical. Galaxies are constantly moving, constantly colliding, and constantly merging, reshaping one another in slow-motion cosmic ballets. Even our own Milky Way is not immune. In fact, it's already on a collision course with our nearest large neighbor, Andromeda, a meeting that will completely reshape both galaxies in the distant future. On the largest scales of the universe, galaxies are not just drifting randomly through space. They move in great, sweeping currents, flowing toward regions of stronger gravity like leaves carried along invisible cosmic rivers. And one of the most mysterious of these gravitational rivers leads directly towards something colossal, something hidden, and something that we still don't fully understand. Astronomers call it the Great Attractor. Our Milky Way galaxy, along with thousands of others, is being drawn toward this enigmatic region of space. The entire local group of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller dwarf galaxies, is moving at an astonishing 600 kilometers per second toward a specific point in the sky near the constellations Norma and Centaurus. This massive gravitational pull affects not just us, but entire clusters of galaxies across hundreds of millions of light years. It's as though an unseen hand is tugging on the cosmic web, pulling everything subtly but persistently in its direction. But what exactly is doing the pulling? That's where the mystery begins. When astronomers first mapped the motion of nearby galaxies in the 1970s and 80s, they noticed that something was off. Galaxies weren't just expanding away from each other due to the Big Bang, they were also drifting in a particular direction, toward a region of space that seemed to contain an immense concentration of mass. The problem was that when telescopes were turned toward that part of the sky, they couldn't see much of anything. The reason? The Great Attractor lies behind the plane of our own galaxy, a region astronomers call the zone of avoidance. It's a part of the sky heavily obscured by the Milky Way's dense clouds of dust and stars, making it nearly impossible to observe invisible light. The glare of billions of nearby stars blinds our instruments, hiding whatever lurks beyond. To peer through that cosmic curtain, astronomers turn to radio waves, infrared, and X-ray observations, wavelengths of light that can pass through the dust. And what they found was astonishing. Behind that veil lies a massive region of space filled with galaxy clusters, dominated by one in particular, the Norma cluster, located roughly 220 million light-years away. This enormous cluster, together with other dense regions nearby, forms part of an even larger superstructure of galaxies known as the Laniakea supercluster, the vast cosmic continent in which our Milky Way resides. The Great Attractor itself appears to be a gravitational focal point within the supercluster, a region of such overwhelming density that it bends the motions of galaxies across hundreds of millions of light-years. The total mass involved is estimated to be equivalent to tens of thousands of Milky Ways combined. Yet even with our most advanced instruments, the full nature of the Great Attractor remains elusive. It's not a single object like a black hole or a cluster. It's a region of mass concentration, perhaps shaped by the overlapping gravitational influence of multiple galaxy clusters and filaments in the cosmic web. Adding to the intrigue, beyond the Great Attractor lies an even massiver structure known as the Shapley supercluster, containing more than 8,000 galaxies. Some astronomers now believe that our motion isn't just toward the Great Attractor, but ultimately toward Shapley itself, suggesting that the Great Attractor may simply be one stepping stone on an even grander gravitational highway. This discovery reframes our understanding of cosmic structure. The universe isn't a static grid of galaxies. It's a dynamic, interconnected web where gravity sculpts motion on scales so vast it takes billions of years for its effects to unfold. Every galaxy, every cluster, every supercluster is part of this flow, drawn into vast patterns of attraction and expansion that weave together the universe's large-scale architecture.
But perhaps the most haunting aspect of the Great Attractor is its invisibility. We know it's there because of its pull, not because we can see it. Its presence is betrayed by motion, by the way galaxies stream toward it like water flowing down an unseen slope. It's an invisible force shaping the visible universe. In that way, it mirrors the deeper mysteries of cosmology itself, unseen influences like dark matter and dark energy that govern how galaxies form, move, and survive. And indeed, this leads naturally to the next profound realization. The Great Attractor's pull reminds us that gravity is not just the story of visible matter. In fact, most of the gravitational glue that holds galaxies and clusters together isn't visible at all. It comes from a shadowy substance we still don't understand: dark matter, the mysterious backbone of the universe. When we look at a galaxy, we see a magnificent swirl of light, stars, nebulae, glowing clouds of gas. But what we see is only a thin veil of the truth. The visible matter, the part that shines, is merely a fraction of what's really there. The vast majority of a galaxy's mass is invisible, existing as something we cannot see, touch, or directly detect. This mysterious, unseen substance is known as dark matter, and it is one of the greatest enigmas in all of science. Astronomers first stumbled upon the idea of dark matter not through sight, but through motion. In the 1930s, Swiss astrophysicist Fritz Zwicky was studying galaxies in the Coma cluster, a massive collection of hundreds of galaxies bound together by gravity. When he calculated how fast those galaxies were moving, he found something shocking. They were orbiting far too quickly to be held together by the visible mass of stars and gas alone. By all rights, the cluster should have torn itself apart long ago. There simply wasn't enough visible matter to generate the gravitational pull required to keep everything bound. Zwicky concluded that some form of missing matter, matter that didn't emit light, must be present, exerting the necessary gravitational force. Decades later, in the 1970s, astronomer Vera Rubin made similar discoveries while studying the rotation of individual galaxies, including our own Milky Way. She found that stars in the outer regions of spiral galaxies were moving just as fast as those near the center. According to Newtonian physics, stars farther out should orbit more slowly because they experience less gravitational pull from the mass concentrated near the center. But they didn't slow down. They kept moving at the same astonishing speeds. It was as if each galaxy were embedded in a vast, invisible halo of matter, providing the extra gravity needed to hold everything together. That invisible halo is what we now call dark matter, and its gravitational influence is immense. In fact, it's the dominant form of matter in the universe. Roughly 85% of all matter is dark matter, the stuff that makes up stars, planets, gas, and even us, the ordinary matter made of atoms, accounts for only about 15%. That means that everything we can see, every galaxy, every star, every glowing nebula, is just a trace of the true structure of the cosmos. Dark matter doesn't emit, absorb, or reflect light, which is why it's invisible. It doesn't interact with electromagnetic radiation at all, meaning telescopes, no matter how advanced, cannot see it directly. It doesn't clump like ordinary matter, it doesn't form stars, and it doesn't collide with itself the way gas clouds do. The only way we know it exists is through its gravitational effects, how it bends light, shapes galaxies, and sculpts the large-scale structure of the universe. To visualize it, imagine that every galaxy you see in the night sky is like a glowing seed surrounded by a massive, invisible sphere. Its dark matter halo, spanning hundreds of thousands of light years. These halos are the scaffolding of the cosmos. They are the skeletons upon which galaxies form and evolve. In the early universe, dark matter clumped together under gravity, forming dense regions that acted like wells into which ordinary matter fell. Gas collected there, cooled, and eventually condensed into stars and galaxies. Without dark matter, galaxies as we know them might never have formed at all. And yet, for all its importance, we still have no idea what dark matter actually is. It doesn't fit into the standard model of particle physics, the framework that explains all known particles and forces. It's not made of atoms, protons, or neutrons. It's not black holes or faint stars or cosmic dust. It's something entirely different. Something that passes right through us and everything around us without leaving a trace. Over the years, scientists have proposed numerous candidates for dark matter particles. Some theories point to WIMPs, weakly interacting massive particles, hypothetical particles that rarely interact with normal matter except through gravity. Others suggest axions, ultra-light particles that could collectively behave like dark matter. More exotic ideas include sterile neutrinos, or even modifications to our understanding of gravity itself, though the latter remains controversial. Experiments deep underground like the Xenon, Lux, Zeppelin, and Super CDMS detectors are actively searching for hints of dark matter particles passing through Earth. Astronomers, meanwhile, study galaxy clusters and gravitational lensing, how light bends around massive objects, to map where dark matter must be. The evidence for its existence is overwhelming. The mystery lies in its nature. If we could somehow make dark matter visible, the universe would look utterly transformed. The night sky would reveal immense, ghostly structures, filaments and halos connecting every galaxy in a vast, three-dimensional web. The luminous galaxies we see now would appear merely as bright beads of light, strung along this invisible framework, marking where dark matter's gravity gathered ordinary matter into cosmic structures. This invisible scaffolding gives the universe its shape, its order, and its stability. It's the silent architect of galaxies, clusters, and the very patterns of the cosmic web. Every star you see owes its existence to dark matter's gravitational blueprint. And yet, the more we learn about dark matter, the more profound the mystery becomes. It's not just that we don't know what it is,
We don't know why it exists or how it fits into the deeper laws of physics. It is, quite literally, the shadow side of creation, the unseen half of reality that holds the visible half together. But dark matter is only part of the cosmic architecture. When astronomers mapped out where galaxies gather and where they are sparse, they discovered that the universe isn't randomly arranged at all. It forms an enormous, interconnected cosmic web where galaxies and dark matter are woven together across billions of light years into one grand structure, the very skeleton of the cosmos itself. When astronomers began mapping the universe in 3 dimensions, plotting not just the positions of galaxies, but their distances, they expected to see something like a random scatter of points, as though galaxies were sprinkled across the cosmos like stars in a night sky. What they found instead was far more structured, far more intricate, and infinitely more beautiful. The universe, when seen on its grandest scales, is woven together like a vast cosmic web, a network of immense filaments made of galaxies, galaxy clusters, and dark matter all stretching across billions of light years into one grand structure, the very skeleton of the cosmos itself. When astronomers began mapping the universe in 3 dimensions and rendered the data in 3D, the result was breathtaking, a pattern that looked almost organic, like the branching of neurons in a brain or the delicate structure of soap bubbles clustering together. The resemblance between the cosmic web and neural networks isn't just poetic, it's a genuine similarity in mathematical structure. The universe, on its largest scale, resembles a cosmic mind, its filaments like synapses through which matter and energy have flowed for billions of years. And at the intersections of these filaments lie the galaxy clusters, the universe's great cities. Each one can contain thousands of galaxies bound together by gravity and dark matter. From these hubs, the filaments stretch outward like highways of stars, connecting one cluster to another across immense distances. The structure continues as far as our telescopes can see and likely far beyond, repeating the same patterns on ever larger scales.
If you could somehow step outside the universe and look at it as a whole, a godlike perspective impossible for us to attain, you would not see a uniform field of galaxies. You would see a spiderweb of light, glowing faintly against an infinite darkness. You'd see luminous filaments bridging across cosmic voids, twisting and branching like tendrils of lightning frozen in time. You'd see vast walls of galaxies, hundreds of millions of light years long, like the Sloan Great Wall, one of the largest known structures in the observable universe. And beyond that, more walls, more filaments, stretching endlessly until they blur into the horizon of what light can reach us. But this web isn't static. It's alive in a cosmic sense. Over billions of years, gravity continues to pull matter along these filaments, feeding galaxies and clusters like rivers feeding lakes. The voids, meanwhile, expand as matter flows out of them, growing larger and emptier. In this way, the large-scale structure of the universe evolves like a living organism, expanding, thinning, and transforming as time unfolds. The reason this cosmic web formed in the first place lies in the early universe, in the tiny fluctuations in density that existed shortly after the Big Bang. When the universe was only a few 100,000 years old, it was filled with a nearly uniform fog of hydrogen and helium gas. But there were minute variations, tiny overdensities where gravity was just slightly stronger. Over billions of years, these small differences acted like seeds. Gravity amplified them, pulling matter into those denser regions while leaving other regions emptier. Dark matter played the starring role in this process. Because it interacts only through gravity, it began clumping first, long before ordinary matter cooled enough to form atoms. These clumps of dark matter became the scaffolding for galaxies to form upon, the bones of the cosmic web. Ordinary matter followed the dark matter's lead, gathering where it had gathered, cooling, igniting, and forming the galaxies we see today. The result of billions of years of this gravitational sculpting is what we now call the large-scale structure of the universe, a pattern so vast and complex that it defies simple comprehension. Each filament can span hundreds of millions of light years.
Each node can contain thousands of galaxies, and each void between them can be larger than the entire observable portion of our local galactic neighborhood. What's astonishing is that the cosmic web is self-similar, meaning that no matter what scale you look at, the patterns repeat. The clustering of galaxies resembles the clustering of stars within galaxies, which in turn resembles the clustering of matter within molecular clouds. It's a fractal-like hierarchy that hints at deep, universal principles governing how gravity organizes matter on all scales. And this web is still forming. Even now, matter continues to flow along the filaments, feeding galaxy clusters and merging them into ever larger structures. Over the next billions of years, these clusters will grow even more massive, while the voids will grow emptier and darker as cosmic expansion stretches the universe further apart. When we map the cosmos in this way, it's almost impossible not to feel awe. We see that galaxies are not random, they're connected, part of a larger, ordered whole. The universe is not chaos, it's structure, it's rhythm. It's an intricate pattern of creation and emptiness that echoes across unimaginable distances. And just as the filaments bind galaxies together, the spaces between them, the vast, silent voids, give the universe its depth and contrast. They are just as important to the cosmic tapestry as the luminous threads that frame them. To understand the full story of the cosmos, we must look not only at where galaxies are, but also where they are not. Between the brilliant filaments of the cosmic web, where galaxies cluster and the universe seems alive with light, lie the true vastness of the cosmos, the voids. These are the immense, silent regions that make up most of the universe. Huge stretches of almost nothingness where galaxies are few and far between, and the darkness reigns supreme. While the bright knots and threads of the cosmic web often capture our imagination, it's the voids that define the universe's scale, its emptiness, and its mystery. Each of these cosmic voids can span hundreds of millions of light years across. Some are so large that if you place the entire Milky Way at their center, it would be isolated, no neighboring galaxies visible for hundreds of millions of light years in any direction. These vast expanses are not entirely empty. A few faint dwarf galaxies or lonely gas clouds may drift within them, but compared to the dense filaments and clusters that make up the cosmic web's skeleton, these regions are deserts of space, places where matter is almost absent. One of the most famous examples is the Boötes void, a staggering structure discovered in 1981. It stretches nearly 330 million light-years across and contains only about 60 known galaxies, when, in a volume that size, astronomers would normally expect to find tens of thousands. The Boötes void is so immense that if the Milky Way were positioned at its center, we would not have discovered other galaxies until the invention of large telescopes. We would have looked into the night sky and seen almost nothing at all. These voids aren't anomalies, they're the dominant feature of the universe. The more astronomers map cosmic structures, the more it becomes clear that most of the universe's volume is empty space. The luminous matter, the galaxies, clusters, nebula, and stars, make up less than 5% of the total composition of the cosmos, and even that matter is concentrated along thin filaments. The rest of existence is darkness and distance, an ocean of nothing through which light rarely travels. It's easy to imagine the universe as crowded, full of stars and galaxies packed together like jewels in a cosmic crown. But the truth is sobering. The vast majority of the cosmos is silent, dark, and empty. If you could somehow travel through the universe, you'd spend nearly all your journey not flying past galaxies, but drifting through this infinite stillness. You could cross billions of light years without encountering a single cluster of stars, only the faint whisper of background radiation left over from the Big Bang. But these cosmic voids aren't simply empty holes in the universe. They're essential parts of its structure. Think of the universe like a sponge, with the filaments forming the walls and intersections, and the voids forming the spaces between them. This pattern emerged naturally from the universe's birth. In the early moments after the Big Bang, matter wasn't distributed perfectly evenly. Some regions were slightly denser, and gravity drew material toward them, forming the filaments and clusters we see today, while the other less dense regions were gradually emptied, as matter flowed outward toward those gravitational hills.
Over billions of years, this process created the enormous contrast we observe today, the glowing threads of galaxies and the immense voids in between. Even though the voids are mostly empty, they are not static. They expand as the universe expands, and the matter that does exist within them continues to thin out. Over cosmic time, the voids are growing larger, their borders pushed outward as galaxies fall deeper into the dense filaments. In the far future, as cosmic expansion continues to accelerate due to dark energy, these voids will dominate even more until galaxies become isolated islands floating in a sea of emptiness. In a sense, the voids are the true essence of the universe, the background against which everything else exists. The galaxies, stars, and planets that fill our telescopes are just the luminous exceptions, the fleeting ripples on the surface of an infinite black ocean. The voids remind us of scale, of contrast, of humility. They show us that even in the grandest cosmic picture, existence itself is defined as much by emptiness as by presence. And yet, there's something poetic about this vast nothingness. It's not simply a cold absence, it's the stage upon which all creation takes place. Without the voids, there would be no structure, no filaments, no galaxies. The dark gaps give meaning to the light. Just as silence gives power to music, the voids give context to the galaxies that line their borders. If you were to stand somehow in the center of a cosmic void, a place no human will ever reach, you would see a sky almost entirely black. Perhaps a few distant galaxies would shimmer faintly at the horizon, red-shifted and dimmed by billions of light-years of travel. The universe would seem eerily still, but that emptiness would be deceptive, because just beyond your view, at incomprehensible distances, lie the glowing threads of the cosmic web, the bustling hubs of creation where galaxies collide, stars are born, and life might one day emerge. In that sense, the voids are not just part of the universe's structure, they are part of its balance. They remind us that the universe is not full of things, it is full of space, and that space itself is the canvas upon which everything else is painted.
But the cosmos hasn't always looked this way. In its earliest ages, those distant galaxies we now see perched on the edges of the cosmic web were far smaller, more chaotic, and much younger than the grand spirals and ellipticals of today. To truly understand the story of the universe, we must look back to those ancient galaxies, the first to light the cosmic dawn. When we peer deep into space with powerful telescopes like Hubble or the James Webb Space Telescope, we're not just seeing faraway galaxies, we're seeing ancient galaxies, frozen in time billions of years ago. Because light takes time to travel, those faint glimmers from the distant universe are messages from the dawn of creation. They show us how galaxies once looked when the universe was still young, chaotic, turbulent, and raw. And what we see in those earliest epochs is utterly unlike the graceful spirals and structured ellipticals that fill the nearby universe today. The first galaxies were small, irregular, and wild, like flickering cosmic embers, rather than organized pinwheels of stars. They were clumpy, full of intense star formation, and shaped more by violence than by balance. In the beginning, there were no grand spirals or majestic elliptical giants. The first galaxies began to form roughly 300 to 400 million years after the Big Bang, when the universe was still emerging from its dark ages. At that time, the cosmos was a dense fog of hydrogen and helium gas, gradually cooling after the initial burst of expansion. Tiny fluctuations in density created in the very first moments of the Big Bang had allowed gravity to gather gas into small halos of dark matter, forming the first galactic seeds. Inside these dark matter wells, hydrogen gas collapsed and ignited into the first stars, population 3 stars as astronomers call them. These were nothing like the stars we know today. They were enormous, unstable, and short-lived, many hundreds of times more massive than the Sun, blazing with brilliance and burning out in just a few million years. Their explosions, the first supernovas, enriched the surrounding gas with heavier elements, paving the way for the next generations of stars, planets, and eventually life itself. The galaxies that contained these early stars were far smaller than the galaxies of today. Most were no larger than a small satellite galaxy, perhaps a few thousand light-years across, compared to the Milky Way's 100,000 light-year diameter. They were highly irregular in shape,
often just loose clusters of stars surrounded by swirling gas clouds. Collisions between young galaxies were common because the universe was denser and smaller back then. These constant mergers stirred chaos, driving shock waves and bursts of new star formation. The James Webb Space Telescope, with its infrared vision capable of peering through cosmic dust and reaching deeper into time than any instrument before it, has revealed these early galaxies in astonishing detail. What Webb shows us is a universe that was far more active and dynamic than we imagined. Many of the galaxies it observes at 13 billion light-years away are forming stars at rates hundreds of times faster than the Milky Way does today. Some are burning through their gas so quickly that they'll exhaust their fuel within a few 100 million years. Over billions of years, these small, chaotic galaxies began to merge and grow, forming larger and more stable systems. Each collision was both destructive and creative, tearing apart old structures while triggering waves of new star birth. Through this cosmic recycling process, galaxies gradually became more organized. Their random, lumpy shapes gave way to smoother, more structured forms: disks, bulges, and spiral arms. By about 5 to 6 billion years after the Big Bang, the universe had entered what astronomers call the cosmic noon, the peak era of galaxy formation. During this time, star formation across the cosmos reached its highest level. Galaxies were maturing rapidly, transforming from turbulent nurseries into complex, majestic systems we recognize today. Some developed spiral arms, stabilized by their rotating disks of gas and dark matter. Others grew into massive ellipticals through repeated mergers, becoming dense, smooth, and old. The story of this evolution from chaos to structure is written into the light of galaxies themselves. When we look at distant, ancient galaxies, we're seeing blue light dominated by hot young stars. Closer galaxies, older and settled, glow more softly in red and yellow, the colors of cooler, older stars. This cosmic color shift is a timeline of galactic aging. Our own Milky Way is a product of this long evolutionary chain. It likely began as a collection of small proto-galaxies that merged together over billions of years. Evidence of this process still lingers in our galaxy structure. Streams of stars torn from ancient collisions, the traces of swallowed dwarf galaxies, and the layered ages of its stellar populations. The Milky Way we see today, structured, stable, and star-rich, is the culmination of countless cosmic encounters stretching back nearly the entire history of the universe. But the story of galactic evolution doesn't end there. Even as galaxies mature, they continue to change, shaped by the forces that dwell within them. At the heart of nearly every large galaxy lies something so extreme, so powerful, that it bends space and time itself: a supermassive black hole. And these invisible giants aren't just passengers in their galaxies, they help define them. At the heart of almost every galaxy lies a secret, an invisible powerhouse so dense, so extreme, that not even light can escape its grasp. These are the supermassive black holes, and they are among the most mysterious and influential objects in the universe. Far from being cosmic oddities, these titanic entities sit at the centers of galaxies, quietly governing their evolution and structure on scales that stretch for tens of thousands of light years. Our own Milky Way galaxy is no exception. At its core lies a black hole known as Sagittarius A star, or A star, with a mass roughly 4 million times that of our Sun. It resides about 26,000 light-years away from Earth, hidden behind clouds of interstellar dust, visible only to radio and infrared telescopes. And yet, despite its quiet appearance, Sagittarius A star shapes the very dynamics of the Milky Way center, its orbits, its energy flow, and even its ability to form new stars. But our Milky Way's central black hole is modest compared to some others in the cosmos. In galaxies far beyond ours, astronomers have found black holes with masses ranging from hundreds of millions to tens of billions of suns. One of the largest known, at the core of the galaxy Tone 618, is estimated to contain around 66 billion solar masses, a black hole so massive it defies imagination. The event horizon, the boundary beyond which nothing can escape, would span more than 1,300 astronomical units, larger than our entire solar system many times over. The connection between galaxies and their central black holes is profound, even symbiotic. For decades, astronomers assumed these black holes were merely byproducts of galactic formation, a sort of gravitational afterthought. But then something unexpected was discovered: a striking correlation between the mass of a galaxy's central black hole and the mass of its bulge, the dense star-filled core region of the galaxy. The relationship is so consistent across different types of galaxies that it suggests a deep physical link between a galaxy's growth and that of its black hole. This realization changed everything. It meant that galaxies and their central black holes grow together, influencing one another across billions of years. When galaxies were young, their central black holes fed greedily on the dense gas and dust swirling around them. As matter fell inward, it heated to incredible temperatures, producing brilliant quasars, galactic cores so bright that they can outshine their entire galaxies. These early quasars, powered by supermassive black holes, illuminated the infant universe, visible even across billions of light years. But this process of feeding, what astronomers call accretion, did more than make the universe glow. It also regulated galaxy growth. When a black hole consumes too much material, it releases tremendous amounts of energy in the form of radiation and jets, blasting out from its poles at near light speed. In this way, supermassive black holes act like cosmic thermostats, preventing galaxies from growing uncontrollably. They are destroyers and creators at once, nurturing their galaxies by keeping them in balance. This feedback loop between a galaxy and its central black hole, known as AGN, active galactic nucleus feedback, is now thought to be one of the key drivers of galactic evolution. In the early universe, when gas was abundant, galaxies grew rapidly, and so did their black holes. As the black holes grew more massive, their energy output increased, heating and dispersing the surrounding gas. This slowed star formation, allowing galaxies to stabilize and mature. Over cosmic time, this push and pull relationship sculpted the universe into what we see today, a delicate balance between light and darkness, growth and restraint.
Supermassive black holes also shape galaxies through gravity. Stars and gas orbit around them, and their immense gravitational wells help anchor galaxies' central regions. When galaxies collide and merge, so too do their black holes, spiraling inward toward one another in a slow, violent dance that can last millions of years. When they finally merge, they release enormous bursts of gravitational waves, ripples in space-time itself, echoing across the cosmos. Detecting these waves, as instruments like LIGO and Virgo have begun to do, allows scientists to listen to the universe's deepest heartbeat, the collision of its darkest giants. What's most astonishing is that these black holes, invisible by their nature, can briefly become the brightest objects in existence. As matter spirals toward them, it forms a glowing disk, an accretion disk, heated to millions of degrees. These luminous cores are so bright that we can see them shining from billions of light years away, long after the galaxies themselves have faded from view. They are the lighthouses of the distant universe, marking the locations of the first great cosmic cities. Today, most supermassive black holes are relatively quiet, having consumed the bulk of nearby material long ago. Sagittarius A star, for example, is dormant, only occasionally flaring as bits of stray gas fall inward. But even in their silence, these titans continue to hold their galaxies together, shaping their orbits and influencing the dynamics of their stars. They are the still centers of galactic storms, their presence subtle yet essential. If galaxies are the universe's great living systems, then supermassive black holes are their hearts, invisible engines that drive their evolution, regulate their life cycles, and preserve their balance. Through their gravity and their fury, they've helped craft the galaxies we see today, including the one that gave rise to us. And if every galaxy is a potential cradle for life, then each black hole, in some cosmic way, is part of that story too. Because without them, galaxies as we know them might never have formed. But this brings us to one of the most haunting questions of all. In a universe with hundreds of billions of stars and each of trillions of galaxies, how likely is it that we are truly alone? What are the odds that somewhere out there, life has taken root under a distant sun, wondering the same thing? When you step back and grasp the sheer scale of the cosmos, the trillions of galaxies, each holding hundreds of billions of stars, The next question becomes impossible to avoid. Are we alone? It is perhaps the most profound question humanity has ever asked, one that bridges science, philosophy, and wonder. Because if even a fraction of those stars host planets, and if even a fraction of those planets can sustain life, then the universe should be teeming with it. To understand just how staggering the odds are, let's start with what we know. The Milky Way galaxy alone contains an estimated 100 to 400 billion stars, and thanks to modern astronomy, especially discoveries from missions like Kepler, TESS, and now JWST, we've learned that planets are common. In fact, they're the rule, not the exception. Nearly every star we observe appears to have at least one planet orbiting it, and many have multiple. That means our galaxy alone may contain hundreds of billions of planets, possibly more planets than stars. Now, among those planets, not all can support life as we know it. Some are too hot, others too cold. Some are gas giants without solid surfaces, and others orbit erratically around unstable stars. But even if we apply the most conservative filters, limiting our search only to those planets that are roughly Earth-sized and lie in the habitable zone, the region where liquid water can exist, the numbers remain mind-bending. Astronomers estimate that in the Milky Way alone, there could be tens of billions of potentially habitable planets. And when you multiply that by 2 trillion galaxies across the observable universe, you end up with a number so large it borders on the surreal. Quintillions of potentially life-supporting worlds. That's more than 1 billion trillion planets where conditions might be right for chemistry to become biology, and for biology to become consciousness. To put that in perspective, imagine every grain of sand on every beach on Earth again, not as stars this time, but as planets capable of harboring life. Even if life emerged on only a small fraction of those, the universe should be brimming with alien ecosystems, oceans under distant suns, forests of unimaginable color, skies lit by strange moons and rings. The Drake equation, proposed by astronomer Frank Drake in 1961, was one of the first serious attempts to estimate the number of intelligent civilizations in our galaxy. The equation considers factors such as the number of stars with planets, the fraction of those that could support life, the likelihood of life-developing intelligence, and the lifespan of communicating civilizations. Even using cautious values for each term, the results often yield dozens or even thousands of intelligent civilizations in our galaxy alone. And if we extend that logic to the entire universe, the potential numbers explode beyond comprehension. But what's fascinating and humbling is that we have no proof yet of any life beyond Earth. Despite decades of searching, the universe remains eerily quiet. Radio telescopes listening for alien signals have detected only the natural hum of the cosmos, and so far, no unmistakable whispers of intelligence have reached our ears. This silence is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "If the universe is so vast and life is so probable, where is everybody?" There are many possible answers to that haunting question. Maybe intelligent life is rare, so rare that we are one of the few civilizations to arise, a cosmic anomaly in an otherwise silent sea. Or maybe life is common, but intelligent, technological life is fleeting, burning itself out quickly, leaving behind the ruins of ambition. Another possibility is that the universe is full of life, but distance and time are the barriers that keep us apart. Civilizations may rise and fall long before their signals can reach us. But the probability remains overwhelmingly in favor of life existing elsewhere, because life, as far as we can tell, is not miraculous. It is inevitable given the right conditions. On Earth, life appeared astonishingly early, almost as soon as the planet cooled enough for liquid water to exist. That suggests that if the ingredients are there, water, energy, and organic chemistry, life will find a way. And those ingredients are everywhere. Organic molecules, the building blocks of life, have been found in interstellar clouds, on comets, and on distant moons like Titan and Europa. Liquid water exists beneath the icy crusts of moons orbiting Jupiter and Saturn. Exoplanets with thick atmospheres and stable temperatures have been identified orbiting stars both near and far. The more we learn, the more it seems that the cosmos is primed for life. Now, imagine what life beyond Earth might be like. Some might resemble us. Carbon-based organisms adapted to temperate worlds orbiting yellow suns. Others could exist in completely alien forms, life that breathes methane instead of oxygen, or that thrives in oceans of ammonia beneath dim red stars. On some worlds, evolution may have taken completely different paths, leading to beings beyond our capacity to imagine, creatures that sense magnetic fields instead of light, or civilizations that communicate through pulses of radiation rather than sound. And somewhere, maybe on a planet circling a distant star in another galaxy, intelligent beings might be asking the same question we are, wondering whether they too are alone. The numbers tell us we shouldn't be. The statistics are overwhelming, the universe too vast, and the conditions for life too common for us to be unique. Even if only 1 in a billion galaxies harbors a civilization like ours, there would still be thousands of civilizations scattered across the observable universe.
But numbers alone aren't proof, and the silence between the stars remains one of the greatest mysteries in existence. The distances separating us from other worlds are almost unimaginably vast, and the speed of light, the cosmic speed limit, may make communication across those distances nearly impossible. Which brings us to the next great dilemma of the cosmos, the communication problem. If life is out there, and the odds say it almost certainly is, why can't we hear it? Why can't they hear us? The idea that the universe could be teeming with life is exhilarating, but it comes with a sobering truth. We may never know it. Despite the mind-shattering number of stars, planets, and potential civilizations out there, the reality of cosmic communication faces barriers so immense that they may be impossible to overcome. The silence we experience, the cosmic quiet, may not be evidence of loneliness, but of physics itself. Let's start with the most obvious challenge: distance. Even our closest neighboring star system, Alpha Centauri, lies about 4.37 light-years away. That means if you sent a radio signal to any possible listener there today, it would take more than 4 years just to arrive. If they replied immediately, you'd wait another 4 years for their answer, an 8-year conversation, just to say hello and hear hello back. Now expand that thought to the scale of the Milky Way. Our galaxy alone is over 100,000 light-years wide. A signal sent from one side would take 100,000 years to reach the other. That means if an alien civilization on the far end of the galaxy transmitted a message when human beings were first discovering fire, it would just now be arriving at Earth. And we, in turn, would need to send a reply that wouldn't reach them until another 100 millennia had passed. At those scales, communication becomes almost meaningless. Civilizations could rise and fall long before their messages ever arrive. A culture might reach a technological peak, send out a beacon to the stars, and then vanish before anyone hears them. This is the synchronization problem. The odds that two civilizations not only exist in the same galaxy, but exist at the same time and have the technology to communicate. The universe is 13.8 billion years old, and intelligent life, if it appears at all, may only last a few thousand or even a few million years before extinction, evolution, or transformation into something unrecognizable. The lifespan of technological civilizations is likely a brief spark on a cosmic timescale. For two of those sparks to overlap in time and space, and for their messages to cross the void at just the right moment, requires an extraordinary coincidence. Even if two civilizations did exist simultaneously, they'd face another obstacle: the speed of light. It's the cosmic speed limit. Nothing, not even information, can travel faster. That means even advanced civilizations bound by the laws of physics can't outpace light's finite crawl across the universe. The dream of instant galactic communication or interstellar travel may be forever out of reach. To grasp this limitation, imagine trying to speak across not just oceans or continents, but galaxies. The nearest large galaxy, Andromeda, is 2.5 million light-years away. A message sent today would take 2.5 million years to reach any potential listeners there, and their reply would arrive 2.5 million years later. That's a 5 million year round trip, longer than the entire history of the human species. Even if we had the power to send messages across the universe, the conversation would move slower than evolution itself. There's also the issue of detectability. Our radio signals, for example, have only been leaking into space for a little over a century, barely 100 light-years in every direction. That's a tiny bubble in a galaxy 100,000 light-years across. Beyond that small sphere, Earth might as well be silent. To any distant observer, we simply don't exist yet. And conversely, if alien civilizations use different technologies, laser communication, neutrino pulses, gravitational waves, or methods we can't even imagine, our instruments may be blind to their signals. It's entirely possible the universe is alive with messages, but we lack the senses to perceive them. Then there's the sobering thought that many civilizations may choose to not broadcast at all. Some scientists have suggested that intelligent life might be aware of the dangers of announcing its presence in a vast, unknown universe. This idea, sometimes called the dark forest hypothesis, suggests that civilizations stay quiet to avoid detection by potentially hostile species. In that analogy, the cosmos becomes a dark forest where everyone hides in silence, hoping not to be found. So the silence may not mean we are alone. It may mean everyone else is listening, just like us, waiting for someone to speak first. And yet, despite the vastness, despite the silence, we continue to search. The SETI programs, Search for Extraterrestrial Intelligence, still scan the skies listening for narrow-band radio signals, searching for patterns that nature wouldn't produce by accident. Newer missions like Breakthrough Listen use powerful radio telescopes to monitor millions of stars, hunting for any sign of artificial transmission. Perhaps someday a signal will come. A faint pulse buried in cosmic noise, a message sent from a civilization long gone, or one just beginning to bloom. If that day comes, it will be the most transformative moment in human history, because that single message would prove that life is not unique to Earth, that consciousness has blossomed more than once in the cosmic ocean. But even if that signal never comes, even if the silence stretches on forever, the question itself gives meaning to our existence. The very act of listening to the stars, to the void, is a testament to the curiosity that defines us. We may never hear another voice in the cosmic dark, but our desire to understand, to reach outward, is what makes us remarkable. And in truth, we are already connected to the cosmos in a far deeper way than communication alone, because we are made of its elements, born from the same stardust that form the galaxies and black holes we gaze upon. Our cosmic address, our place in this vast hierarchy, reminds us that we belong to something unimaginably greater than ourselves. We begin here, on Earth, our fragile blue world, the only place we know that cradles life. It is a small sunlit sphere wrapped in thin air where oceans shimmer and clouds swirl, orbiting quietly in the warmth of its parent star. Every mountain, city, forest, and human story exist on this one delicate marble. Earth is home, not just to us, but to billions of species, each one a thread in the grand tapestry of life that has evolved over 4.5 billion years.
But Earth is only a tiny member of the solar system, a vast collection of worlds and moons orbiting our star, the Sun. Our solar system spans nearly 6 billion kilometers from the Sun to Neptune, and far beyond that lies the realm of icy bodies in the Kuiper Belt and the distant Oort cloud, where comets drift in frozen slumber, sometimes for millions of years. The Sun itself is just one star among hundreds of billions in our galaxy, a modest yellow dwarf that, from a cosmic perspective, shines with unremarkable light. Zoom out further, and we find ourselves inside a spiral arm of our galaxy called the Orion Arm, a minor branch between two major arms of the Milky Way galaxy. Here, our solar system drifts about 27,000 light-years from the galactic center, orbiting once every 230 million years, a single cosmic year in the life of the galaxy. The Milky Way's glowing disk stretches roughly 100,000 light-years across, a grand spiral of gas, dust, and hundreds of billions of stars. Its luminous arms sweep through the void like a celestial whirlpool, rotating slowly and gracefully through time. At the heart of the Milky Way lies Sagittarius A star, the supermassive black hole that anchors the galaxy's structure, around which every star, including ours, ultimately revolves. The Milky Way itself is home to thousands of star clusters, massive nebulae where stars are born, and immense dark clouds that hide the promise of future suns. But even this glorious galaxy is just one among countless others. Together with Andromeda, our nearest large galactic neighbor, and dozens of smaller satellite galaxies, the Milky Way forms a gravitational community known as the Local Group. This cluster spans about 10 million light-years across and contains over 80 galaxies of varying sizes, some grand spirals, others faint dwarfs with only a few million stars. The Milky Way and Andromeda are the titans of this group, and in about 4 billion years, they'll merge into a single colossal galaxy. But our local group doesn't float alone. It's part of an even larger cosmic structure called the Virgo supercluster, a vast collection of galaxy clusters spanning roughly 110 million light-years across. The Virgo supercluster contains thousands of galaxies arranged in filaments and sheets of light, all bound loosely together by gravity. Our local group sits near the outskirts of this giant, moving slowly inward along the cosmic filaments that feed it. And yet, even the Virgo supercluster is only a part of something still greater, the Laniakea supercluster, the immense gravitational basin that encompasses more than 100,000 galaxies spread over 520 million light-years. The name Laniakea comes from the Hawaiian words for immense heaven, a fitting title for a region so vast it defies human comprehension. Within Laniakea, all galaxies, including the Milky Way, flow along gravitational pathways toward a mysterious central region known as the Great Attractor, that immense mass concentration we discussed earlier. If you could see Laniakea as a whole, you'd witness a sweeping landscape of cosmic filaments stretching like veins across space, with galaxy clusters shining as brilliant nodes along those threads. The Milky Way would be just a speck of light among 100,000 others, each one a galaxy, each containing billions of stars, each possibly home to worlds like ours. And yet even this colossal supercluster does not define the edge of our home. Beyond Laniakea lies the rest of the observable universe, the largest address we can meaningfully describe. This is the cosmic horizon, everything we can possibly see or detect, a sphere roughly 93 billion light-years in diameter. Within it are an estimated 2 trillion galaxies, each with hundreds of billions of stars. Beyond that horizon, the universe continues, but its light will never reach us. At this scale, the hierarchy of our cosmic address becomes staggering. Earth, a blue planet, cradle of life. Solar system, 8 planets orbiting one average star. Orion Arm, a spiral branch of the Milky Way galaxy. Milky Way galaxy, 100 billion stars, one of trillions. Local group, a family of 80+ galaxies bound by gravity. Virgo supercluster, thousands of galaxy clusters, 110 million light-years across. Laniakea supercluster, our immense heaven over 500 million light-years wide. Observable universe, 2 trillion galaxies stretching across 93 billion light-years. And beyond that, the unobservable universe, the infinite unknown stretching forever into the cosmic dark. Each level is an exponential leap in scale, a revelation of just how small our world is. Earth, which feels so vast to us, our cities, our wars, our oceans, our histories, is less than a speck of dust in a single galactic swirl, itself one grain of sand on an infinite cosmic shore. Yet within that grain of sand lies something extraordinary: consciousness, awareness, the ability to comprehend this vastness, to map it, to name it, to feel awe in the face of it. When we say our cosmic address, it's more than just a coordinate. It's a story of belonging. From Earth to the edge of the observable universe, We are part of an unbroken chain of existence. Every atom in our bodies, every breath we take, comes from this cosmos, from stars that lived and died long before us. The iron in our blood, the calcium in our bones, the carbon in our DNA, all were forged in the hearts of ancient suns. We are literally made of stardust, citizens of the Milky Way, residents of Laniake, and children of the universe itself. But even this cosmic identity is not fixed. The universe is expanding, and not just expanding, but accelerating, driven by an invisible force that will one day pull galaxies so far apart that even the stars themselves will vanish from sight. Ever since Edwin Hubble's groundbreaking discovery in 1929, we've known that the universe is expanding, that galaxies are moving away from us, and the farther they are, the faster they recede. At first, astronomers imagined that gravity, the great cosmic glue, would eventually slow this expansion down. Perhaps they thought the universe might even stop expanding someday and begin to collapse inward again, a grand reversal of the Big Bang known as the Big Crunch. But in the late 1990s, something astonishing shattered that assumption. Two independent teams of astronomers studying distant exploding stars called Type A supernovae found that those faraway galaxies were not slowing down in their retreat, they were speeding up. The universe's expansion wasn't just continuing, it was accelerating. Something unseen, something mysterious was pushing space itself apart, overpowering the pull of gravity. That something is what we now call dark energy, a force that fills all of space, driving galaxies apart faster and faster as time goes on. And it doesn't just affect the distant cosmos, it's acting everywhere right now, stretching the very fabric of space between every galaxy, every cluster, every atom of the universe. To grasp this, imagine the universe as a balloon with galaxies embedded on its surface. As the balloon inflates, the galaxies move apart, not because they're traveling through space, but because the space itself between them is expanding. Now imagine that inflation speeding up, the balloon stretching faster and faster, driven by an invisible energy that no one can see or measure directly. That is what our universe is doing right now. Dark energy is unlike anything we've ever encountered. It makes up about 68% of the total energy content of the universe, dwarfing both ordinary matter, about 5%, and dark matter, about 27%. And yet, we have no idea what it actually is. It could be a property of space itself, a kind of cosmic pressure that increases as the universe grows. Or it could be something more exotic, a field that permeates reality in ways we cannot yet comprehend. Whatever its nature, its effects are undeniable. It's pushing galaxies away from each other at an ever-accelerating pace. Right now, galaxies that are already very distant are moving away from us at speeds approaching the speed of light. As time passes, those galaxies will move so far and so fast that their light will become redshifted, stretched to longer and longer wavelengths until it fades beyond detection. One by one, galaxies will disappear over the cosmic horizon, vanishing not because they've died, but because their light can no longer reach us. In a few decades of billions of years, this process will isolate our local group of galaxies, those gravitationally bound together like the Milky Way, Andromeda, and a few dozen smaller companions. These will eventually merge into a single massive galaxy, sometimes called Milkomeda, surrounded by an expanding void. Everything else, the 2 trillion galaxies we can see today, will have redshifted away into invisibility. For any future civilizations living in that distant era, the sky will look heartbreakingly empty. They will see only their local galaxy group floating alone in a sea of black. There will be no clues left that the universe ever contained anything beyond it. The cosmic microwave background radiation, the faint afterglow of the Big Bang, will have stretched to wavelengths so long that it will fade completely from detectability. The evidence of the universe's origin and expansion will be gone, erased by time and distance. Those future astronomers, even with the most powerful telescopes imaginable, might believe their galaxy is the entire universe, just as we once thought the Milky Way contained all of creation. They will live in a cosmic island, surrounded by eternal darkness, cut off forever from the wider cosmos that once was. It's a haunting image, and yet it tells us something profound about the era in which we live. We exist at a unique moment in cosmic history when the light from other galaxies still fills our skies, when the universe's past is still visible, and when we can still see the echoes of the Big Bang itself. We are cosmic witnesses to a fleeting age of clarity, a time when the universe has revealed its vastness to us before closing the curtain for good.
And what happens after that distant future, when the universe grows even older? If dark energy continues its work unchecked, galaxies will drift farther and farther apart until the stars themselves begin to die. Trillions of years from now, new stars will cease to form as gas is exhausted. The brilliant galaxies of today will fade into darkness, their remnants swallowed by black holes. The universe will grow colder, quieter, a cosmic winter spreading slowly across eternity. Yet, even in that far future, the story of the accelerating universe will still echo in the atoms of our existence, because it was this expansion, this delicate balance between gravity and dark energy, that allowed galaxies to form, stars to ignite, and life to arise in the first place. We owe our very existence to the same cosmic forces that will one day scatter everything we know into infinite darkness. And this realization, the fragility and temporariness of our cosmic moment, leads us to the final truth, one that brings every piece of this journey together, the humbling conclusion of what it means to live in such a vast, expanding, and ancient universe. In the end, after journeying across 2 trillion galaxies through time, matter, darkness, and light, we arrive home, back to our pale blue world, orbiting a modest star in the outskirts of an ordinary galaxy. And with that return comes a quiet realization that everything, every moment, every heartbeat, every civilization, every dream, has unfolded in a single, fragile corner of the universe. All of human history, the rise and fall of empires, the creation of art, the building of cities, the wars and the triumphs, the acts of love and cruelty, has taken place on a small planet orbiting one of 200 billion trillion stars. From the cosmic vantage point, the Earth is less than a grain of dust suspended in a sunbeam that itself is one faint flicker in a boundless ocean of light. And yet, that grain of dust is special beyond measure, for within it, matter has learned to reflect upon itself. Through us, through our minds, our questions, our awareness, the universe has achieved the remarkable. It has become self-aware. We are stardust that can wonder about the stars. We are atoms that can contemplate their own origins. In every one of us burns a tiny spark of the cosmic fire that began nearly 14 billion years ago. Carl Sagan once said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." That statement isn't poetic metaphor, it's literal truth. The carbon in our bodies was forged in ancient stars that lived and died billions of years before the sun was born. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were born in supernova, scattered across the galaxy, and eventually gathered into the dust cloud that became the solar system. In a very real sense, we are the children of stars, the living continuation of their light. And so when we study the cosmos, when we map galaxies, measure starlight, or ponder dark energy, we are in fact exploring our own story. The universe isn't out there, it's us. It's the grand unfolding narrative of existence, and we are both its observers and its participants. This realization should humble us. It should strip away arrogance, pride, and the illusions of separateness. And yet at the same time, this perspective doesn't diminish us, it deepens us. For even in all its immensity, the universe produced consciousness, creativity, compassion, and curiosity. Out of the raw chaos of physics and gravity, life emerged. Out of life, intelligence. Out of intelligence, wonder. That means that every act of kindness, every discovery, every work of art, every question asked in awe, these are not trivial. They are the universe expressing meaning through us. We are not insignificant because we are small. We are significant because we are aware. A universe without observers might exist, but it would have no one to experience its beauty, to ponder its mysteries, to give it voice. Through human eyes, the cosmos sees itself. Through our instruments, it measures its own vastness. Through our minds, it contemplates eternity.
Think of what that means. For billions of years, the universe expanded in silence, its galaxies forming and colliding, its stars burning and dying, all without witness. And then, on a small planet orbiting a quiet star, a species evolved that looked up and began to wonder. In doing so, we gave the universe something it had never had before: meaning. So yes, on the scale of galaxies and superclusters, our concerns are infinitesimal. Our entire civilization could vanish and the cosmos would continue undisturbed. But the fact that we can recognize this truth, the fact that we can feel both humbled and inspired by it, is what makes us extraordinary. We are the only part of the universe we know of that can look back at itself and say, I understand. This perspective, this cosmic awareness, should change how we live. It should teach us reverence for our world, compassion for one another, and gratitude for the fleeting moment we share in the light. Because, against all odds, in a universe of infinite darkness, we were given the gift of consciousness and the chance to see the stars. Everything we are and everything we will ever be is a brief, shining note in the vast symphony of existence. One day, our sun will die, our galaxy will merge, and even the light of the cosmos will fade. But for now, in this fragile slivered time, we exist. We breathe, we think, we love, we wonder. That in itself is enough to fill eternity with meaning. So as we look out into the endless sea of galaxies, 2 trillion and counting, let us remember this. We are not separate from the universe. We are the universe, awake and alive, daring to understand itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.